Good morning, students. Today we're going to do section 7.3 on slope fields. This is going to be a new concept for us. However, it does relate directly to the differential equation. So go ahead and hit pause and work through this warm-up. Okay, so you had a chance to look at the warm-up. I kind of tried to trick you here on this first example. Um, so how do we know we have to find the general solution? Well, when you see general solution, you think you're going to have a plus c in it. But I have to solve the differential equation if possible. Right now, it's not officially a differential equation. We need to rewrite this as dy dx. And you might notice we do have some terms that are linked together. However, there isn't any amount of algebra that I can do to separate the x and the y. And this is a tricky one. So I do want you to understand that some differential equations we're not able to use algebra by solving. When I isolate the x and y together, I only can move it over using multiplication or division. Watch what happens here if I try this. Now, this is incorrect, so do not write this down. But if I was to try to move this over, I would have dy dx minus y squared equals negative x. Now, notice I can't just move the dx over here because that affects this problem. So there isn't any amount of algebra that we can do that will get a dy and an x combined together so we can do the integral. So in this case, it is not possible. Now, just because a differential equation is not possible to solve doesn't mean we can still, we can't stop using it. We can use this information to help us analyze some other things, kind of like question number 2. So using the differential equation number 1, write the equation of the tangent line. So right there, I'm thinking equation of a tangent line, right? But we know our m is dy dx. So that whole slope is given by this equation right here. And I need to write the equation of the tangent line given the point x1, y1, and the slope. Well, the only thing that I need to do now is I need to find the slope at the given point, negative 2, 1. Well, to do that, I'm going to use the fact that y prime, or dy dx, is the slope, and we're going to use the points that are given. So it says take y and square it and subtract 1. Well, y1 is 1, x is negative 2, and when I simplify that, I get y prime equals 1 plus 2, or y prime equals 3. And remember, that is the slope at this given point. So to write the equation of the tangent line, I know my slope. My slope is 3. I know x1, y1. And technically, I could leave it like that. I'm officially done here. This is the equation of the tangent line. If you want to do some algebra, you could multiply the 3 and bring the 1 over, and you get the same answer here. I recommend leaving it in this form because if you make a mistake algebraically, they're not going to count it as accurate. So what are we doing today? Our goal is to look at some differential equations and introduce this idea called a slope field. Now, I'll let you know this is kind of a lot of work. This is the main problem for our notes today. We've got multiple parts, so take really good notes here. Pause the video as you need. So consider the differential equation dy dx equals x times y minus 2. Now notice how this one is slightly different than the warm-up. I can isolate the y minus 2. I can divide both sides by y minus 2 and then solve. We're not going to do that yet, but I know that this one is a potentially separable differential equation. Now, what are we going to do? We're going to introduce this idea of a slope field. And we know what slope is, right? Slope is dy dx, but what is this idea of a slope field? Well, a field is all of the slopes for every xy pair that we can write down. So what we're going to do is this, and actually I'm going to get rid of that and show you how. Now, if you have graph paper at home, we want you to use graph paper. If you do not have graph paper, that is fine. You have to be very accurate on this, though. All right, so what you're going to do then is you're going to make an XY pairing, and we're going to go ahead and label my axes. And I want to go 3 units, 1, 2, 3. And you don't technically need to label every one, but label one of them so the person reading knows the scale. And then do your best to get the same scale, same width, going the other direction. And then I'm not sure how high we're going to go, but we're going to use X values. Now, the X values we're going to use are going to be the X's that we plug in here, and the Y's that we use are going to be the Y values. So every ordered pair has a point. Now, I'm not sure how many points I'm going to need for this. So what I'm going to do is I'm going to make a dot at each one of these spots. And I want to find the slope for each one of those. And it's going to be a lot for this example. But notice, every single dot, I'm not going to go up to 4. We'll go 3 in each direction, and that'll be good enough. So for your homework tonight, unless they tell you otherwise, go 3 in each direction, and we'll find the value of those points. And then I want to go 1, 2, 3. And you know what? This isn't perfect, so I'm going to erase these numbers. And the reason why is I want these dots to appear so you guys can see what we mean when we say the slopes. Okay, so what did I do? I went 3 in each direction, 3 up, 3 down, 3 left, 3 right, and I put dots representing every whole number pairing. Now, what I want to do is I want to make a table for these because I need to find the slope for every single point. Okay? Now, remember what dy dx is? Slope. Hence the name slope field. Now, there are some patterns that you can use on this. Once you understand what x and y are doing, you might be able to make this a little friendlier. But here's what I'd recommend. We know that we're going to start here. I'm going to write, it's no great way to do this. Maybe I'll put -3 right here. I'm going to start with the uppermost point, or I'm going to start when x is -3 and y is +3. Okay, that's this dot right here. So what do I need? I need to find the slope at that point. Okay, well, in this case, dy dx is the slope. I know what x and y are. I'm going to plug in -3 times 3 minus 2. See how I plugged in -3 here for x and 3 here for y? And then I just need to simplify. And you do not have to show this work because we're going to do all of these points. But you can see that that's how we generate the slope. So -3 times 1 tells me I have a slope of -3. All right, and then I'm going to go to this next point. Now, I'm not going to do anything with that slope yet, but let's go to this next point. And we got -3 over -3 up 2. And I'm going to generate that slope. So -3 and 2. Plug -3 in for x and 2 for y. And then I get 0 here. -3 times 0 is 0. And then we're going to go to the next point. That's this point right here. So -3, -1, and so on. I'm sorry, -3, +1. Almost made a mistake. That's this point right here. So plug in -3, plug in +1, and you see you get -3 times -1, which is a +3. Okay. Now, what I want to do is I want to get all the points when x is -3. Those are 1, 2, 3. And don't forget about 0. Right? 0 is a value. And then I'm going to get ones when we have -1. So that's this point. This is a point when y is -2 and -3. So pause the video. I'm going to do the same and fill out that chart. All right. So here are all of the possible points. I shouldn't say possible, but all the points that I have. These are the slopes. So what are we going to do with these slopes? Well, at each one of these ordered pairs, negative 3, 3, I'm going to graph a tiny little, as if it was a tangent line. I'm going to graph a tiny little slope there, and I want that to be negative 3. So how do we do that? That's the hard part, right? So at this point, right, ooh, well, I'll highlight it, but at that point, that's where these two values are going to have a slope of negative 3. So I want to draw a little line that goes down 3 over 1. Now, we don't want to, I mean, you can see our page is going to get filled up quite a bit here very quickly. So let me make this as simple as possible. Okay, don't draw this yet, but I'm focused on this point. Now, I want a slope of negative 3. So what if I went down 3, so 1, 2, 3 over 1. Imagine that there's a point here, and I'm going to connect this point to this point. That would give me a slope of down 3 over 1. So I'm going to kind of pretend like I'm drawing a line there, except for I'm going to draw a tiny little line, just a segment through that point. And that is the slope, m equals negative 3. Right? So this point has a slope of negative 3. Now let's go to the next point. Okay, let's go to negative 3, 2, and let's graph a slope of 0. So if I go over negative 3 up 2, I have a 0 slope. So we're just going to draw it straight across. It's a horizontal line. And then I have to have a slope of positive 3 at the point negative 3, 1. So go over negative 3 up, positive 1. And now I need a positive 3 slope. So think of this. If I'm at this point right here, and I go up 1, 2, now I'm going to estimate 3 over 1. Pretend there's a point right here. And I want to connect this point to give me a slope of positive 3. So then I'm going to draw a rough sketch right there. And there's the slope at the point negative 3, 1. So what about 3, 0? That's positive 6. Now again, we're estimating, right? If I say that this slope is 3, 6 would have to be twice as high and over 1. So I'm going to estimate that slope to be about a positive 6. Now notice, it's definitely greater than this. If I call this 3, this is greater. All right, so this would be about a 6. I mean, we're not perfect here. Right? If we were in class, I would show you differently with a ruler, but we're not. So now we get negative 1, that's me, negative 3, 1, and I have a slope of 9. And notice the slopes are getting bigger and bigger and bigger. So if I'm at this point, go over negative 3, down 1, I need a slope of 9. Well, that's really hard to draw. I just want to make it so it's more steep than the one I drew before. And then what would a slope of 12 be at the point over negative 3, down 2? It just has to be a little bit more steep than what I did before. And then 15 is going to be steeper. So, notice when the numbers get much larger, it's really hard to draw the difference between a slope of 6, a slope of 9, a slope of 12, and a slope of 15, which is why it's kind of important sometimes to have a table. All right, now, that's fun, right? But we're not done. All of that was for when x was equal to 3. But what about when x is 2? What about when x is 1, negative 1, negative 2, 0, 1, 2, and 3? We got to do all of these. All right? So we're going to take a little bit. What I'd like you to do is make a table. And some students are thinking, I'm not going to do that. I'm going to do it in my head. If I go over negative 3, up 1, over negative 2, up 1, 2, 3. So if x is negative 2 and y is 3, you could generate that slope and get 1 times negative 2, and then know that this slope right here is a negative 2 slope. So I'd go down 2 over 1, and I would draw a line like that roughly. I like these different colors. I'm going to create a table just because it's hard to show you guys what we're doing, and then I'll do it for all the rest of these. But you guys go ahead and hit pause and work through it yourself. All right, so if you look at this, I took all the values when x is negative 2, and then all the values when x is y right here. And then I plug them in. Now, here's what I did, and you might notice this. If x is always negative 2, right here, and you know you're going to have -2 times, and then with your y value, all you have to do is 3 minus 2, so that's 1, and 1 times -2 is -2. So then I'm going to take this value at the point -2, 3, so go over -2, up 1, 2, 3, and I need to draw a slope that is -2. So I'm going to pretend if I start here, I go down 2 over 1, and then I'm going to pretend there's a line connecting this point to this point. And that just gets me kind of the steepness. It's not perfect on a computer. I don't love that. So I don't love that either. I want to go from here to here. That's not great, but that's my slope of -2. And then at the point -2, 2, I get 0. Now you might notice something. I will give you a little hint. Notice if y is 2, what happens when y is 2? Well, 2 minus 2 is always 0, so it doesn't matter what x is, which means I don't care which x value you're at. If y is equal to 2, you will always have a 0 slope. And that's a pattern. So if you see patterns in these slope fields, which eventually that's what we're going to be focusing on, then you're going to be able to save yourself a ton of time. All right, so then I got the next one, go over -2 up 1, and that has a slope +2. So I'll go from this point I'll go up 2 over 1 and draw a line, and there's a slope of +2, and then continue that on. So here I got a slope of 4, which would be up 1, 2, 3, 4 over 1. So I'm going to just draw an estimated line here. And notice these slopes keep getting larger and larger and larger. So I'm just going to kind of make them fairly steep. And again, it's really hard to tell the difference between a slope of 10 and a slope of 15 on a value like this. All right, hopefully that's enough where you guys can finish your slope field. I'm going to pause it and work through the rest of it. So here's my values when x is equal to -1. You can double check your slopes, and then I graphed each slope as we went along. Okay, I'll do the next one. All right, I'll show you where I was at with this one. Well, what about when x is 0? When x is 0, I started making my table, but then I realized there's a pattern here. Right? When x is 0, it doesn't matter what y is, right? 0 times anything will give me a slope of 0. So you don't need to show any of this work in the table. And then what you're going to do is you're going to draw a 0 slope, which we already have one here. But you're going to draw a 0 slope anytime x is equal to 0. All right, so you want to make sure that if there's a pattern, you see that pattern and apply it. We had a pattern going this way when y was 2, and a pattern when x was 0. So I'm going to actually not use the 0 chart and then go on to my other values. So notice there's a pattern here when x is equal to 1. If x is 1, then all I'm doing is taking the y value minus 2. So you can generate these very quickly. And then let's go ahead and graph. Over 1 up 3 has a slope of +1. So I want a slope of +1 here. So I'm going to think up 1 over 1, and that'll give me a slope that looks roughly like that. We already know this slope is 0. And then I got a slope of -1. So I want to go down 1 over 1, get my slope of -1. Then I got a slope of -2. So I'll go down 2 over 1 and kind of estimate that point. And then we got the slope of -3, 1, 2, 3 over 1. Kind of estimate that. It should be steeper than the one before it, 4 and 5. Okay. Here's my work for when x is equal to 2. You can double check your work, but check your slopes, and it should be roughly the same. And then we just got the last one when x is equal to +3. And you can go ahead and do that work, and then just have your final slope field all produced. Okay, so there's my slope field, and notice I picked all of these points. Now, when you do the homework, I think I'm going to recommend you don't pick as many. This is a lot. We did a lot of work here to produce this slope field. Usually on the AP test, they'll have like 6 points that you'll have to pick. Some of them involve interesting factors, like when x is 0 or y is 2. So it involves something like this. All right, well, how can we use this information to help us out? This is a graph of the slope field. So what we're going to do now is we're going to pick a point kind of at random, but I'm going to pick this point 1, 1. Now notice in my table, if I show the work, what is the slope at 1, 1? The slope at 1, 1 is negative 1. So if I go over 1, up 1, I know that that slope right there is negative 1. I want to draw what's called a solution curve through that point. This is where it becomes very tricky. Let's see if I can pick a nice color that pops. So my solution curve is going to be a line that goes through that point, but it represents the general function of this. Now, notice this dotted line right here, those are all zero slopes. Well, if they have zero slopes, then we kind of know that that's a horizontal asymptote in my graph, which means the function will never cross this line. So picture this. If I start at this point and I draw my slopes, as I get closer, if I was to pick a point right here, let's say negative 0.5 up 1.5, if I plugged in 0.5 here for x and 1.5 here, I could calculate the slope, but I know it's going to be just a little bit positive, but not as positive as this one. And then as I get closer here, it's going to get closer to 0. And whenever I cross the line when x is 0, I know that at this point, my solution curve has to have a 0 tangent. But then it starts to go negative as I go past this. So what we want to do is we want to estimate the solution curves. Notice how I'm not connecting dots, right? We are not connecting a point to a point. We're following what we think the solution curve might look like. Right? So it's going to go up here. Why? Because all of these are positive slopes. So it's going to have positive slopes going up. And then it's going to have a 0 slope when it crosses x equals 0. And as it gets closer to 0.11, then we're going to have a negative 1 slope. And then my slopes get more and more negative. And it should follow, roughly be parallel to points near it. Right? So see how this slope is roughly parallel. It doesn't have to be perfect because we're freehanding this, but that line is roughly parallel to that line. So this blue line right here is called the solution curve. Now, you might look at that as, wait a minute, doesn't that kind of look like a parabola opening downward? And that could be. We're going to actually see what kind of function it is. But now, I'm going to just bring this part down here. This was the differential equation from above. Now we're going to make the connection to the stuff that you guys have done in the past. Right? So let f be a function that satisfies the given differential equation. What they're basically saying is let f and y equal the same thing. Right? You can write y equals or f equals. Now we have to write the equation of the tangent line. Wait a minute, didn't we just do that? We did that in the warm-up. Here's x1, y1. Now, notice, you don't have to do any more work. We already know the slope. At the point 1, 1, didn't we just have that? At the point 1, 1, my slope is negative 1. Okay, so if you have a table, go ahead and steal that. I know my slope is negative 1 from the table. I know the point x1, y1, so I'm going to write the equation of the tangent line. Let's make this blue. x1, y1, so 1, 1. Slope is negative 1, and you could stop right there if you want, or you could distribute and simplify. The reason why I'm going to distribute and simplify is because it says then use your line to estimate the point 1.2. So actually, it might be easier to simplify it in right here. If you just plug 1.2 in, that might be pretty quick. But I'm not sure a lot of students would do that, so I'll distribute first. And then when I add 1 over here, I get 2. Now, that's the equation of the tangent line. Remember, that's roughly equal to the function itself. They told us that above. So I want to approximate or estimate f of 1.2. Well, all I'm going to do is take my tangent line, and we're going to plug in 1.2. Simplify. And usually this is something that we would do without a calculator. So the approximation of the point 1.2, the output, when x is 1.2, the output is 0.8. That's my approximation or my estimation. Okay, so now how do I check that, right? Because this was what the tangent line would tell me the value is equal to, but what about the actual particular solution? So now we're going to take this given differential equation, and we're going to do all that same work. This is really good stuff to review for tests and quizzes. So we're going to find the particular solution using the initial condition, x being 1 and y1. So why don't you go ahead and do this? I'm going to separate the variables as my first step. I have to divide by a 1 over y minus 2. And then I have x dx. If you feel confident right now, go ahead and pause and try to work through this on your own. Okay. Now we have to do the antiderivative. Well, what I would do on this side is I have a u substitution. If you've done this enough, you know that it's the natural log. But if you haven't, then you're just going to have to take the derivative. There we go. Take the derivative of both sides, and notice we get du equals dy. So then I get 1 over u du. And when I take the derivative of 1 over u, that's the natural log of u, but instead of u, I'm going to replace it with y minus 2. Over on the right side, we end up with a pretty friendly one. This is where we just add 1 up top, and I get x squared plus c. Okay. So the next thing we're going to do, as soon as c appears, now you're going to use the initial condition. So my goal next is to find c. And we've done all this a ton of times. So I'm going to plug 1 in for y right here. I'm going to plug 1 in for x. And then we're going to solve. So I get the natural log of -1. Notice this is where the absolute values come into play, because officially that turns into the natural log of +1, which we know is 0. That's really big. And then here we get 0.5. And then solve for c. I get c equals 1/2. Okay. Now, I'm going to take this -1/2 and plug it in right here to find the particular solution. Okay, so now this is set up where I have to get y by itself, so I'm going to raise both sides to the power of e. That we reduce out the natural log. We still have to deal with that absolute value. And this isn't super friendly. I'm just going to leave it like that. Nothing comes down, no tricky properties that I want to mess around with. So the question now is, well, what has to happen? If x is 1, y has to be a positive output. So this whole thing has to end up being positive. I'm going to keep that in mind as I solve this. So notice, I would add 2 over to this side. But this answer will always be positive because it's an exponential function, which means the only way I'm going to get a +1 out of this is if this value is negative. So now here's where the absolute value sign comes in, this sign and this sign. I'm going to make that negative so this condition is true. And then we're officially done here. So the last step is now use your solution to find the actual value of 1.2. Notice, this was the estimate or the approximate. So now we're going to find the actual value of f of 1.2. Remember, y is equal to f. And then at this point, I would just grab my calculator. Make sure all of that is in parentheses. So grab your calculator, simplify the top. All right, so when I plug in 1.2 to the actual particular function that we just found, here's my answer. Now notice, the next question is compare your answers from the approximate 1.2 found in part C to the actual value of 1.2 in part D. Was your estimate in part C an under or an overestimate? So my approximation is an overestimate. And I'll show you on your slope field why that is the case. So if we go to x equals 1.2, so estimating, here's x equals 1.2 roughly. What if I drew a tangent line in there? Right, so let's just pretend that this spot right here is x equals 1.2, and if I follow that up, here's my spot. Now notice, where would the tangent line come? It would be about right here, and the actual value is going to be below because this function here is concave down, and the tangent line is above, so therefore, whatever value we get using our tangent line will always be an overestimation. So if you're going to explain this, you want to say something about the fact that the original solution is concave down and our tangent line would be an overestimation. Okay, so you can kind of see that both in the values here, you can definitely see that our estimate is overestimate versus the actual value, and you can see it in the slope field as well. Okay, a couple of things here. This is just getting at, you don't really need a slope field. This is the slope field for the differential equation x over y to determine when does differential equations produce a positive slope. Well, let's think about the ordered pairs, right? Well, what do you know? If my answer is going to be positive, what has to be true about both x and y? So when does the differential equation produce a positive slope? Well, let's look at it. You can see that I've got positive slopes in this first quadrant. When x is positive and y is positive, all of these slope fields, all the slopes are positive. And then over here, they're negative, negative, positive. So why is that true? Why is it positive in quadrant 1 and quadrant 3? So I guess I'll answer this. Quadrant 1, quadrant 3. And the reason why, and this is the important part, why do I produce positive slopes? X and y are the same sign value, right? If x is positive and y is positive, your answer is positive. If x is negative and y is negative, your answer is positive as well. So reading the equation and the behavior of the function itself can tell you why things are going to work the way they are. Well, what about this one? Why do I have negative slopes? Right? Every slope in this quadrant is negative. Same thing in quadrant 4. Right? Quadrant 2, quadrant 4, we have negative slopes. Because x and y are opposite signs. Well, when do we have zero slopes? Let's take a look at that one. Well, a zero slope clearly has to equal 0, which means the bottom value can be any number, but the top has to be 0. So where do I have 0 slopes? We have 0 slopes anytime x is equal to 0. And you can see that. Where is x equal to 0? Right here. And notice every single one of them has a 0 slope except for when x is 0. So we got to say anytime, that's me. I think anytime x is equal to 0 except when y is equal to 0. Because if y is equal to 0, I get the indeterminate form. So I do have to make a disclaimer. Anytime x is 0, but then I'm over here, I'm just going to put y cannot equal to 0 because that's officially undefined right here. And then the last one, notice something here. This is kind of important. I'll use red. When do I have an undefined slope? Well, what has to be true for an undefined slope? An undefined slope is whenever we divide by 0. So I don't care what number I have on top. I cannot divide by 0. Now, think about what an undefined slope looks like. An undefined slope is a vertical line. Now notice, when y is equal to 0, they didn't put the vertical lines in, and the reason why they don't have vertical lines is because it's really hard to draw a perfectly vertical line, and people might misinterpret that. So they just leave them blank. So if you ever see blank spots like this, that means that the function is undefined. If you were to put vertical lines in on the AP test, they would still give them to you. All right, but why, or I should say where, do we have undefined slopes? Anytime y is equal to 0, and then the answer is why is that true? Because we cannot divide by 0. So make sure you're able to tell where and explain the why. The why is just as important. All right, well, what if I'm looking for a solution here? So let me get rid of this part. And what if I pick some different spots on this graph? And I want to draw a solution curve. Well, what type of family of solutions are we looking at? There we go. It depends on the point. What if I pick a point right here? Okay. Now notice, I'm not picking a perfect point. I'm going to pick the spot over 2.1 up 1.8. I'm just kind of making that up. Actually, 1.8 would be right up there. Right? Now, where's that going to go? Well, first off, I notice that there's a line here. This is called a slant asymptote that you guys have seen, which means I can't cross that. So my function is going to go really close to that, but it's never going to cross it because once it hits this slope, it's going to stay that slope forever. And then here, I'm going to have slopes that get closer and closer to these orange slopes. And then they have to be vertical here, so I'm going to have a slope straight up and down. And then I'm going to have a line that kind of dances in between these. And notice I'm not really connecting dots. I'm just following the slope curve. So this looks like a branch of the hyperbola. And that could be the family of solutions. Now, what if I picked a different point? What if I picked a point up here? Let's say I picked 0, 3. Okay, well, I know that its slope is 0 here, and then it's going to be parallel to the slopes it's close to. It's going to follow that curve. And it's going to go this way. So if I pick a different point, this kind of looks like a parabola, right? Now, with hyperbolas, this could be a second branch of it. So maybe that's built into another piece of this graph. But then notice you also have this slant asymptote here. So I know I'm never going to cross those lines. All right, the last piece here for this one is let's find the differential. Let's find the general equation. Well, what do? Take the given differential, separate your variables, just like we did a while ago, and we're going to solve. Okay, so this should be the fun part. The quick review, separate y. I'm going to bring y up here with dy. So I'll multiply by y to both sides. I'll leave x there, and then I'm going to find the antiderivative of each side. So we get y squared, but I'm going to put a 1/2 out in front, get 1/2 x squared plus c. And then since we're just looking for the general equation, you could stop here, but we want to get practice solving for y. So I'm going to times both sides by 2 to get rid of the 1/2, and that will leave me with an x squared. And then remember, the c kind of absorbs that. The c stands for any constant, so if I times it by 2, it's still a constant. Now, here's the tricky part. I have to get rid of the squared, right? I'm going to take the square root of both sides. I don't know which value I'm going to take. Is it going to be the plus or the minus? And since it's the general solution, we don't have a specific point to check which value we should take, so we have to put the plus and the minus. Now, if you were to graph this on a calculator, just try graphing, notice if you take the square root of x squared, if there wasn't a plus c, that would just be the linear portion here. Anyways, all right, sometimes you're given a lot of information, right? So here's the function for the differential equation. They show the slope field, that was given. All they want us to do is sketch possible solution curves. So this is just getting used to the fact that we're not just connecting dots, right? And there might be a different one if I do the spot 3, 2. So I'm going to start at 0, 1, 2, 3, up 1, 2, and I'm going to follow this curve. So notice this is a positive slope. I want to be as parallel as I can to the slopes that I'm close to. And then same thing here. And notice you're almost like running into a line, and then you start to flatten out. Okay, now notice this is a horizontal asymptote right here. You cannot cross things when you have a zero slope, which means I'm getting closer and closer to having a zero slope, so this is going to just flatten out. And then if I go the other direction, I have another horizontal asymptote, which means I cannot cross that, right? And if you were to do this, okay, that's a big error right there. They would not give you credit for that if you were trying this on an AP test. Because we have to understand that my slope is going to get closer and closer to 0, but it's never going to officially cross. And there's the solution curve for the point 3, 2. So what if I had picked a different point? What if I told you to do it for 0, 8? Well, I'm going to go over 0, up 8, 6, 7, 8. Now notice here, kind of start off with this slope. It's going to follow the same trends. I want to be parallel to the green ones, and then parallel to the purple ones. This is just going to keep going up. And then we're going to come down, and notice we're getting close to that asymptote, so I'm never going to cross it. But I'm going to get really close to it. And that's my solution curve for the second piece. Okay. Why don't you pause this one and go ahead and just decide which, based off of the slope field, which equation could this be for? Okay, well, what I would do is pick a random point. Pick any point. Let's pick this one. And draw your solution curve. If I start off here, it's going to start curving up, 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 up. And then this is going to go down. I have to be parallel to the slopes that I'm near. And then notice these slopes are getting very steep. Well, what function does this look like? To me, this looks like some type of x to the third value, right? It's not sine, it's not cosine, it's not a parabola, it's not natural log, so the only possible option is 1/6 x to the third. All right, just another quick one. Let's look at this. If I tell you to go to the point 2, 1, actually, we don't have that on this graph. I just noticed that there's numbers here. Let's say we're at the spot 0.5, 0.5. Right, so go over 0.5, up 0.5. That's this spot. Now, I want to be kind of close to these spots, so I'm going to be going up. And then as I follow this, my curves have to follow the trends close to it. And you can see as we go around, this general solution curve would give me a circle. So you could separate your variables. You have to call this dy dx. Move the y over. And then go ahead and find the antiderivative. And you would get your general equation, which would be a circle of some type, which means at some point this value would be squared. You need to have some form of an x squared. But then we take the square root. So I'm not going to go through all that because we already did. I just want to give you a quick overview. Okay, so for homework tonight, it's out of the textbook. I'm going to make your life a little easier here. If you have graph paper, we want you to use it for sure. If you don't have graph paper, now my pen's not working. There you go. If you don't have graph paper, here's what I want you to do. As neatly as you can, I want you to draw some points. And you know what? Let's make your lives a little easier. Let's go 2 units in each direction, top and bottom. So when you make your graph, you have to do the spots at 2, -2, 2, -2, 1, -2, 0, and there. And then all the spots at -1, all the spots when x is 0, and all the spots at 1 and at 2. So instead of going 3 in each direction, let's go 2 in each direction. And if it's up to you, you can make that chart then. Or if you're able to keep it straight in your head, then you could do that without the chart. I recommend writing it. You don't have to show this work here when you're calculating the slope. Good luck. Have a great day. Adios.